So welcome to the last video for this section where we're going to talk about non-homogeneous equations. So what I want you guys to do first is start by working on this warm-up, which should be pretty straightforward if you just convert it back to sort of the standard form with two variables. So give that a shot. All right, and let's go over the answer. So if you convert it, you should get x prime equals 3x plus 4 for sort of your first equation, and y prime equals 5y plus e to the t. Right, so these are both just sort of first order linear equations, which we've been dealing with since the very first section. And so we get something like this. I'll go ahead and just, remind everyone the steps for this. So if I have mu here, it's going to be e to the integral of negative 5 dt. So that is our mu, e to the negative 5t. And then we have that e to the negative 5t times y is equal to the integral of the other side times our integrating factor. And we end up with y equals e to the t, or negative e to the t over 4, plus some constant, I'll call it C2, just to not confuse myself later, e to the 5t. Do the same thing for x, right? You should get x equals negative 4/3 plus C1 e to the 3t. And so then we could rewrite this back in our form, in vector form, as follows. All right. So that is our final answer, and sort of the idea behind the warm-up here is for the other sort of cases, for the other non-homogeneous linear systems, what we're essentially going to do is end up converting them to a system that's as simple as this. So we'll say a little bit how to do that as we sort of go on, explain bit by bit. Before we get into sort of the main topic, though, I want to just remind everyone of one particular point. So that is if I'll give these names, so let's call this equation 1. So if the homogeneous system has solution, and I'm going to denote it by x of c because, and that c sort of stands for complementary, which you may remember from when we did second order linear equations. So let's say it has solution, c1 f of 1, f1 of t times some vector v1, and then c2 f of 2 some vector v2. And if we have a particular solution to a non-homogeneous equation, call this equation 2, So the same thing, but I just have, an extra term here. Then the general solution to equation 2 is x of t equals our particular solution plus the complementary solution. All right. So we have these. And so this is going to sort of be an important thing to keep in mind. And with that, let's sort of go into our first example. So we have x bar prime equals some matrix 6, 8, 1, 4 times x plus the vector 2e to the t negative e to the t. And because this is sort of a first problem, just to get the idea, we're going to use the fact that 2e to the t negative e to the t equals e to the t 2 negative 1, and 2 negative 1 is an eigenvector of our matrix. All right, so just like the general case, we're going to go ahead and find the complementary solution first. And I'm going to skip some of the details here. So remember, we find our characteristic polynomial, which after putting it out, we should be able to factor as lambda minus 2 and lambda minus 8 equals 0. We find then our two eigenvectors. So for lambda equals 2, we end up with the system that looks like this. And we end up then with the eigenvector 2, negative 1. And for lambda equals 8, we end up with the eigenvector 4, 1. Okay. So if we wanted to, not totally necessary, but we could write our complementary solution. C1 e to the 2t, 2 negative 1, plus C2 e to the 8t, 4, 1. Okay, so one thing to check, yes, 2, negative 1 is an eigenvector. It's one of the ones, and it has eigenvalue 2. Okay, so we found our complementary solution. We're going to look for our particular solution. And what we're going to do here is use our hint. So the idea is, right, is that we have an eigenvector here, and sort of the key thing is, right, if I multiply my eigenvector to 6, 8, 1, 4, I'm going to end up with just a multiple of my eigenvector. So this is what this is going to enable us to do. So let's look for a solution of the form xp of t equals, let's say, h of t times 2, negative 1. Okay. Now, if this was any other vector, we would be screwed. However, let's see what happens. So, right, we're going to have xp of t equals 6, 8, 1, 4 xp of t plus e to the t 2, negative 1. So if I'm sorry, that should be a prime. So if I put it, remember I'm just taking the prime of the derivative, so I'm going to end up with h prime of t times 2, negative 1. And then here, I bring this inside just to verify that this does indeed happen. We look at what happens here. So we're going to have, right, in the first coordinate 6 times 2, so 12h, and then minus 8h, and 1 times 2h, minus 4h. Okay, so that becomes 4h and negative 2h. And if I want to pull this out, I'll pull out a 2h so that I get back what I started with. So 2h, 2, negative 1, plus e to the t 2, negative 1, h prime of t 2, negative 1. Okay, so I'm going to explain it sort of one level deeper, but it should be somewhat clear to at least some of you what's going to go on just from the way I've written this. So, right, this is a system of equations. So I have 2h prime equals, and then on this side, 4h of t plus 2e to the t. And in the bottom one, I get negative h prime equals negative 2h minus e to the t. So the key thing, right, is I end up with really the same equation twice. I mean, I've just multiplied through by a constant. So if I divide the top by 2, right, I get h prime equals 2h plus e to the t. And if I multiply through the bottom by negative 1, I'm going to get h prime equals 2h plus e to the t. Okay, so take a look at this, and waiting for the screen to cut back in, sort of what we started with. So this equation here, which is both of them essentially, is sort of represented here if I just kind of ignore the same vector 2, negative 1. So really all that we're going to do is now solve h prime equals 2h plus e to the t. So, jumping ahead a little bit, e to the negative t dt, and we should get, normally we would have to include a constant, but because we can just sort of find a particular solution, we're not going to worry about that. And we should get h equals e to the negative t, integral that, you get negative e to the negative t, and then times 2t leaves us with negative e to the t. Okay. So with that said, right, remember what our original form was. So we look for a solution of this form, which tells us that our particular solution is negative 2 e to the t and e to the t. All right, so the only thing left to do is write our general solution of x of t equals our particular solution. And if I want to make it a little bit easier to read, I can pull out an e to the t there. Plus our complementary solution, which let's remind ourselves what that is. We have it right there, c1 e to the 2t, 2 negative 1, plus c2 e to the 8t. And that is our general solution. All right. So let's look now at a slightly more complicated one. All right, so we'll solve something like this, and hopefully in a second. Oh, let me double check that. Yeah, that should be positive. And yeah, everything else looks good. Okay, so normally this is upping the difficulty a little bit. The reason why I wrote it in this form should hopefully be clear in a second. So if we go ahead, find the characteristic polynomial, we should end up with lambda minus 5 times lambda plus 3. So lambda equals 5. We should end up with the eigenvector 2, negative 3, I mean among others. And for lambda equals negative 3, we should end up with 2, 1. All right, I'm not going to write the complementary equation most of the time. Most problems it's going to be optional. So let's just go forward. Now, we're going to try to use the same trick we did last time. So the key thing to note about the non-homogeneous part of our equation. So we have negative 4t, 6t, and 2e to the t, e to the t. Right, so if we want to commit to this eigenvector, this is negative 2t times this vector, 2, negative 3, and then plus e to the t, 2, 1. Okay, so another thing to note is that if I could solve these parts individually, and that's essentially what I'm going to do. So the same sort of principle applies, right? If xp1 is solution to something like this, and xp2 is solution to something like this. So the same thing, except, well, okay, I'll use F there and G there. Then if I add the two solutions together, right, I get a solution to the same problem, but with F and G added together. So it's that same principle of superposition that we saw in part 2 of this class. And we're going to use it again. Okay. So because of this, though, we're going to split it up into two parts. So we're going to look... Oops. So we're going to look for a solution of the form, I'll say h of t times our first eigenvector of 2, negative 3, and then some other function, I'll call it g of t, times our second eigenvector. And really, what we're going to do is we're going to find some h of t, which is just going to give us this part because it matches the corresponding eigenvector. So we're going to have, xp first equals h of t to negative 3. And so then we have, xp prime equals our matrix A, 3, 4, 3, negative 1. And then instead of the whole solution, it's just going to be the part corresponding to this eigenvector. So that is going to be a negative 2t times 2, negative 3. All right, so we get h prime 2, negative 3 equals and we should know already what's going to happen when we do this multiplication, right? This is the eigenvector for negative 3, so we're going to end up with negative 3 ht times 2, negative 3. I could do the same sort of thing as last time, really view it as two systems and then show at the very end that, okay, the two systems are the same, but let's just skip that step and just jump straight to the next part. H prime equals negative 3h minus 2t. Okay, before I solve that, I want to sort of set up the next part. So let's sort of think about what's going to happen here. Well, I know sort of a lot of the same things are going to happen. The only real difference is, right, my eigenvalue is going to change. So I'm going to have G prime. Let's skip some steps. So I know that when I plug this in, multiply it by the matrix, this has eigenvalue. Let's see, where did we get that? Okay. Oh, apparently I miscopied these. Okay, so this should be -3 and this should be 5. Yeah. Okay. So I have that. This time my eigenvector is going to be 5, g of t times 2, 1, and then plus just the part of my answer that is attached to 2, 1, so plus e to the t. And so, at the same time, I'm going to end up with g prime equals 5g plus e to the t. All right. At this step, these are two pretty straightforward solutions. I'll walk through one just to sort of show exactly what you're supposed to do, but this is a first order linear equation. We've been doing this since the beginning. So for this one, right, h prime plus 3h equals -2t. So our mu is e to the 3t. E to the 3t times h equals the integral from -2t times our integrating factor e to the 3t. We do an integration by parts here. And at the end of the day, we should get that h is equal to -2t over 3 plus 2/9. All right. Do something similar with g here, and we get that g is equal to -e to the t over 4. Reminding ourselves the form of our solution. So remember, this is our particular solution, but we can just sort of go ahead and write down the general form. So we have -2/3 t plus 2 over 9 times that corresponding eigenvector of 2, -3 plus -e to the t over 4 times the corresponding eigenvector of 2, 1, and then plus our complementary solution. All right. So the only sort of difference between this problem and the general case is if you look back at sort of our setup, I kind of wrote it in such a way that it was pretty clear which thing should correspond to like what eigenvector, right? So I tried to separate it in that way. And what we're going to do next is look at a case where that is not so clear. So this should be sort of the most general that we're going to get. With these things, we're always going to have two distinct eigenvalues. The formulas become much more complicated if you have complex or a defective eigenvalue. So we're just going to stick with that. All right, so we get our eigen characteristic equation, lambda plus 3, lambda minus 1, for our eigenvector of, or our eigenvalue of -3. We get an eigenvector of 1, 1. And for our eigenvector of 1, we get an eigenvector of 5, 1. Okay. So now the only problem is we have sort of a 6, -2. Maybe we could pull out a 2, a -2, get like a 3, 1. The problem is that's neither of our eigenvectors. So what we want to do next is write 6 e to the -t, -2 e to the -t in the right form. So we want to write it as, f1 of t times 1, 1 plus f2 of t times 5, 1. And then from there we could proceed exactly as we did before. So it turns out that a really good way of figuring out what these are, I mean, we could just go forward and, try to solve them, right? We have f1 plus 5f2 equals 6 e to the -t, and f1 plus f2 equals -2 e to the -t. So that's like one option. We could try to solve that directly, but if you've taken matrix algebra or you remember what we learned about inverses in part 2 of this class, you know that another way of going about this is actually compute the inverse of this matrix. So I say this matrix, it's not actually clear what matrix I mean. So what we want to do is take both our eigenvalues, just sort of put them right next to one another. The order doesn't really matter, but it is important to choose an order and stick with it. So what we're going to do is compute the inverse of this. And so remember what that means is we swap the diagonal entries. Well, we swap them, they're both 1s, and we make the off diagonal entries negative. And then we divide by the determinant. So 1 times 1 minus 5 times 1, 1 minus 5. Or at -1/4 times 1, 1, -5, -1. And what we do now, right, is if you think about this in terms of writing this as a matrix equation, we want to solve for f1 and f2. All that we do now is take this and multiply by our original vector. So right, so we have -1/4, and then 6 e to the -t plus 10 e to the -t, so that's going to be 16 e to the -t. And then -6 and -2, so -8 e to the -t. Divide through by that -1/4, we should get -4 e to the -t and 2. Okay. So remember, this is our f1 and our f2. And remember, this f1 is associated to, here's where the order matters, right? The way I built this matrix, I put 1, 1 first. So the first entry is the thing you're going to attach to 1, 1. So I'll sort of write that. Again, I'll say xp equals g11 plus 5 or plus h51. I'm not even going to write out the full matrix equation this time. So what we're going to have is G prime equals, and now let's see, 1, 1 was the eigenvector for -3. So -3G, and then plus F1 is the thing associated to 1, 1, and F1 is -4e to the t. Right, I can go ahead and solve that, and I should just get that G is equal to e to the -t. Now for H prime equals, see, H was attached to 5, 1. 5, 1 is associated to the eigenvalue 1, so 1 times H, and then plus F2 to e to the -t. And I should get that H is equal to negative e to the -t? Yeah, I think that's right. Yeah, negative e to the -t. Okay. And if it's not right, I mean, replace whatever you have. I think I might have made a mistake in my answers for this part. But regardless, what we do next is we just write our particular solution. So this, sorry, right here. So e to the -t, 1, 1. Plus negative e to the -t times 5, 1. And then plus C1 e to the -3t, 1, 1. Plus C2 e to the t, 5, 1. And that would be our general solution and our final answer. All right. So I'm going to give you guys this last one as an exercise. And because I just want you to practice sort of the n bits, I'll tell you what the eigenvectors and eigenvalues are for the matrix. So solve x prime of t equals 2, 1, 4, -1 x of t plus 4 e to the t plus 3t e to the t. And as a hint, sorry about the real scribbly writing. I'm pretty sure that this tablet is about to die, so I want to get through this quick. So our matrix 2, 1, 4, -1 has eigenvalues slash eigenvectors as follows. So lambda equals 3 with vector 1, 1, and lambda equals -2 with eigenvector 4, 1. All right, so go ahead and give this a shot. And okay, so I'll work through a little bit more than usual for these exercises at the end. Right, but first what we want to do is figure out how to write this vector in the right form. So we're going to take the inverse. I'll put 1, 1 first and then 4, 1. Compute the inverse matrix where I'll get 1, 1, negative 4, negative 1. Divide that by 1 minus 4, the determinant. And so I'll get negative 1/3 times, well, 1. I'll move the negative inside. 1/3, negative 1, negative 1, 4, 1. All right, so we multiply this by our non-homogeneous part. For e to the t plus 3t and e to the t, giving us negative t and e to the t plus t. Right, so remember what we do next is set up our equation. So I'll do xp equals g 1, 1 plus h 4, 1. We get our two equations. G prime equals the eigenvalue for 1, 1, which was 3, times g, and then plus this first coefficient there, minus t. Setting up the h equation, h prime equals negative 2 times h, and then plus this second part, e to the t plus t. All right, solving this, we should get one solution is g equals t over 3 minus 1/9, and h equals e to the t over 3 plus t over 2 minus 1/4. And then just writing out the final solution, negative 2t 4, 1. We get the following. All right, and we'll end it there.